I'm going to do is pull up the localization and mapping. We had the last two slides to go through. The last but one slide, I might just refer to it because of the shortage of time. But the other one, I want to bring it up on the screen. So we were talking about SLAM, which is one way to localize and also build a map. And I said that this is the technique apparently used by the majority of people. It's called post-graph optimization. It's a very nicely made video from MapWorks by this guy Brian Douglas, who in my opinion is one of the best educators in the world. You know, you should see his the multimedia that he creates. Just so flawless, but he must be putting in hours of work, I'm sure, in doing it. So also there are some associated software files that you can actually run. And he has a video on that also. Here's a separate video that talks about the MATLAB example of post-graph optimization. So if you have time, you know, before the end of tomorrow, which will be the last hours of the class, we can come back and watch this together. Okay, this one I showed the other group. I'm not sure I showed it to this group or one person now, but it's worth looking at because you think of localization as some massive application involving self-driving cars or something, but you'll see what happened to it. So there was a company that assessed all these automated robot vacuum cleaners, just comparing them, because I told you they're like $600, and you know, you'll say, who would pay $600 when I can get some exercise and do it myself, you know, 30, 40 minutes, you know, I get some exercise and I, you know, clean my house, because it's not perfect. So what this company did was they assessed the coverage patterns, because that's the most important thing. You have furniture, you can't clear the furniture to clean up a living room because it's so inconvenient. You have to work around the furniture. So the question is, when the robot, if it has a bump sensor, it hits the furniture, is it programmed to completely reverse and go in the opposite direction, or will it? Because then what will happen is the area around the furniture will be neglected. Yeah. So you can't have like overreaction, right? And some of them are obviously overreacting because you can see that only the white areas have been covered in this big room. So essentially they took about 7 or 8 vacuum cleaners and they obtained the coverage pattern. So also, when a vacuum cleaner is doing its thing, it needs to localize and map, because it has to know where in the room it is so that it knows what part of the room has been done, not keep on doing the same thing. And there'll be certain areas that cannot be reached, so maybe the homeowner can create more space so that it can get in behind sofas. It's a very complicated problem actually. It's basically frontier exploration. The robot is doing frontier exploration, right? Trying to know more about this area, and ideally it has to have 100% coverage. It's not possible, but 80 would be nice. Then the homeowner can come and do the remaining parts on their own. So here are the vacuum cleaners they tested. And here, slightly better, but look at the random way, it's going all over the place. But still, much less than 25% coverage. And then it starts to get better with more sophisticated algorithms. Still spotty, very good. So this seems to be, this is D-Bot, only $400. The other one was $950. That's iBot, the first inventor. $950, $400 D-Bot. Seems to do a much better job. So that's how you gain competitive advantage in a commercial product. You don't just put something out there and fool people, because most people will not be fooled in the long term. You know, they'll figure it out. So they're using the Nito Botvac D6 connected using a LiDAR SLAM system. So it's got a LiDAR based SLAM system, and they're trying to show you, like in the dark, you can see exactly what it's doing, going under the coffee table. Yeah. Not so good. Much better. The $170, see, that's how you win the hearts of your customers. $170 is a pretty reasonable rate, because the regular vacuum cleaners that you push are around about $200, $250. I guess here they're just showing you a hybrid optical mini cameras and laser navigation system. So it's a very nice article. You know, I love collecting articles like this, but after a while they get old and you have to find new articles. Just to show students that this is not just theory that professors are shoving down your throat, and there is more to it. Any questions? Okay, so that's the end of the localization for now. Okay, what's next? So I am going to touch on probability. Have you had probability?
Yeah, no.
You haven't had?
He has.
Oh, you haven't had? It's not compulsory?
It's
I'm
not
not sure
factory,
it's
it's
in
the first
second.
case.
So let's go through the basic concepts of probability rapidly. So what you want to pull up is probability terminology definitions in your Teams folder. Then after that you're going to learn two theorems, the total probability theorem and Bayes theorem, which is one of the most powerful theorems ever created, the Bayes theorem. It's similar to the Kaplan filtering, but I would say its reach is even more than that because it's used in medical diagnostics all the time. So essentially probability is a study of randomness, right? Because most things in this world are random. They are not deterministic, you know. So I often tell my students that when you drive from home, when you get out of your garage, it's not 100% certainty that you're going to return home alive. You know, we always think of it as certain, we take it for granted, but it's really a random event. So maybe the probability is something like 99.99 that you return. When you get into a plane, it's not 100% that you get to your destination. So that was my point, that everything in the real world is random. So first, you have to have the concept of an experiment. So tossing a coin multiple times is an experiment. Drawing a card from a deck multiple times is an experiment. So the concept of probability first has to have an experiment that you define. Then each experiment will have a set of outcomes, right? And the total sample space is a set of all possible outcomes. So in the case of tossing a coin, there are only two outcomes, heads or tails. Drawing a card from a deck, there are 52 outcomes, right? So the experiment determines the outcomes. A robot moving along a line, there are an infinite number of outcomes, right? Because if you go continuous, then between 0 and 100 meters, there can be an infinite number of outcomes. It could be in any one of those spots. Or if you go discrete, you can say I'm only interested in every meter. So then there are 100 outcomes, right? So it depends on the experiment and how we define it. So the simple event is individual outcomes like heads or tails or the jack of spades when you pull a card from a deck. So that's known as a simple event. But the compound events are where you should be interested in, because typically you have compound events. For instance, a robot's X and Y location, right? That's kind of a compound event because there's an X and a Y and there's a combination. So a compound event is made up of a collection of one or more simple events. And examples are following. So tossing a coin, there is no compound event because it's either heads or tails. But tossing a coin 3 times.
Yeah.
So these are the outcomes now, right?
Yeah.
There's no other possibility. PTH means tails, 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 heads, and so on. So event, at least 2 heads, that would count as a compound event. At least 2 heads. Event, exactly 2 heads, that is also a compound event, right? It's all of these and all of these. So once you have the experiment defined, so the experiment is now defined as tossing a coin 3 times. That's what it is. So and because of that, you have compound events. I've given you 2 examples. Roll a die, right? Simple event is outcome of 3 or 4 or 5 or 6 or 1. Even number 2, 4, 6. Okay, then we get to the concept of probability. So this is how probability is ideally defined. That means you do an experiment an infinite number of times. Obviously, it's not going to work in the real world because we don't have enough lifespan to do a million or infinity times, right? We can do 1,000 or 10,000 or 10 million. We can't do infinity. But this is kind of an idealized definition. So the probability of an event A, is taking the limit of how many times A turned out and the total number of trials. And the limit n going to infinity will give you the probability of the event. Now, we can't do that, so therefore we use like 1,000 or 10,000 and say, okay, that's a good way to estimate the probability. That's what you do in practice. Because these numbers you can't get. It's somewhere out there, but we try to approximate it, but by doing like a reasonable number of trials. You can't do 2 trials because then you won't get a reliable estimate. Maybe 10 is not enough. So you figure out that what is that number that you're happy with, in terms of generating the probabilities. A union B. So you can have the union of 2 events. So is the event consisting of all outcomes that are either in A or in B or in both. Now the word "or" is confusing because you say he's either going to see this movie or this movie today. Then you have that impression that it's mutually exclusive, right? Or in that sense is different from "or" here. Here it means union. That means either A or B, or there can be an intersection between A and B. Right? So less than 3 is 1, right? Even number is another. So both of those compound events, they actually intersect. So therefore, A union B is not like the English use of the word "or." Or typically, we say one or the other, but that's not what this is. So if you're familiar with Venn diagrams are an attempt to graphically indicate this concept of events and outcomes, and where A union B sits, next there'll be A intersection B. So you can draw A and B like 2 eggs, and then the intersectional area is called A union. The intersectional area and everything else is known as A union B. The other one is intersection alone, which is the joint event. That means it has to be in both spaces, both eggs, so to speak. So that's smaller, whereas A union B is all of A, all of B, as well as the intersection area. Okay, complement of the event is a set of all outcomes in S. So S is a sample space. You cannot get a sample outside the sample space. You cannot say, hey, guess what? I made a mistake. I have a outcome that is outside the sample. No, then you have to change the sample space and bring that in also. So complement of the event A is like not A, right? So all outcomes in S that are not in A. Mutually exclusive, also known as disjoint, are 2 events A and B that have no outcomes in common. That means if you know A has occurred, then B could not have occurred. So if you know A has occurred, the probability of B is 0. Given that A has occurred, the probability of B is 0. Because they are mutually exclusive. One occurs, the other cannot occur. So I mentioned the Venn diagram, which I just explained. So A union B, can you imagine the Venn diagram, right? With an intersecting area. So that makes, once you look at the Venn diagram, you don't need any more thought. Because that's enough for engineers, that A union B will be both of those, right? But remember, you'll be double counting the intersection. Because if you add the probability of A and B, you'll be double counting the intersection. So it takes away that intersection. So it's actually quite logical that A union B would be like this. If A and B are mutually exclusive, then there's no intersection. Therefore, the probability is 0. So then you can go back here and say A union B is equal to just the sum of those 2 if they're mutually exclusive. Because this can be substituted there for A and B being mutually exclusive, and so you'll get a new result, which is like this, but for mutually exclusive events, because we don't have any overlap between A and B. So here's another example. Roll a die. Even is 3/6, agree? You're assuming it's a fair dice, not biased one way or the other. So low is 1, 2, 3, that's what I mean. P even intersection low. Even intersection low has only 2. Only 2 satisfies that. So it has to be 1/6. P even union low. Right? And now we remember this formula here? This one? So P even plus P low minus P even intersection low. So every engineer should take a course on probability. It's just so important. Maybe everybody should take a course on probability. Yeah. They do?
Yeah, it's compulsory for us. I mean,
All
first year, so I
engineers.
have not taken any.
Yeah. I thought you got through the system somehow. I'm just kidding. So two events A and B are independent. If knowing that A has occurred does not provide any information about the occurrence of B. So that's what independence means. And he's going to come up with an experiment or an example that most people will find it hard to believe. If you toss a coin, right, and you get a certain outcome, heads or tails, next time you toss it, that's unrelated to this. You can theoretically get heads 100 times. You're saying, how is it possible? Should the probability be 50% overall for a good coin, for a unbiased coin? That's right. But the second toss is independent of the first. So it is possible to get heads again. Just having got heads once doesn't mean that the second one, there's less of a chance. So many people think if you win a lottery once, that's it. They're never going to win a lottery again in their lives. There have been cases reported where people have won 3-4 lotteries in the course of a year. Maybe they didn't win anything in the rest of their life. But these events are independent. One does not affect the other. So, picking a card from 2 separate decks of cards, recording heads and tails on 2 separate coin tosses. All of these are independent. So I have one card deck. So here you're tossing the same coin. But if you have 2 card decks and you pick a card here, you can get the same card. It's not affected by you having picked that same card in the other deck. So that's what you mean by independence. So for independent events, right, the probability of occurrence of the joint event can be calculated as just the product. That independence condition is important. If these two are independent, then probability of the intersection is just the probability of one multiplied by the probability of the other. Only if they are independent. As an extension of the above definition of events that are independent, we can say that if two events are mutually exclusive, they cannot be independent. You know why? If they are mutually exclusive, you know that if A has occurred, B could not have occurred, right?
Yeah.
So that's dependence, isn't it?
Yeah.
So therefore they cannot be independent. So we finished with the independent events, right? So let's go to events that are dependent. So that formally means that if the occurrence of one event influences the likelihood of the other event. So for instance, you see a student coming in with a raincoat and he's all wet. So you say, okay, it must have rained. Unless the guy took a shower in the bathroom. You know what I'm saying? So those are dependent events. You see somebody with muddy boots and you say, okay, it's probably rained, So these are examples of dependent events. So drawing 2 successive red cards on a deck, if you do not replace the first card, if you put the card back, those are independent events. I told you, you can get the same card. You can, right? You can do it like 100 times. It's possible theoretically. Those two are not linked. But if you don't put the card back, then there is dependency.
Yeah.
Okay, then conditional probability. Probability of B given A is the probability that B occurs given that A has occurred. So it's mathematically defined like this. So this is a definition, not a derivation. Probability that B occurs given, that vertical line means given A has occurred, is probability of the intersection event over the probability of A. So this is how you calculate conditional probability. You know why? Think of the intersection. That is A intersection B, right?
Yeah.
You know A has occurred. So automatically your sample space is now that intersection area, not the whole thing anymore. Because probability of B given A. So if A has occurred, then you're only focusing on the intersection, right? Because that's how you get B. It can't be the B outside of the intersection. Because you know A has occurred, so now you're focusing on just this part. And therefore it makes sense that it is probability of just the intersection part divided by probability of A. the occurrence of A changes the outlook on the occurrence of B. So we can extend the above definition to the case of independent events, because so this is the definition, but we know for independent events probability of the intersection is the separate probabilities, and then P of A cancels, giving you P of B. Let's go through that again. Here's the definition of conditional probability, and we're talking about independent events. So for independent events, P of A intersection B is just the product of P A P B.
Yeah.
PA cancels and P of B. This makes perfect sense, because if they are independent events, why would the fact that A has occurred change anything with respect to your understanding of the probability of B? Because the two are not related at all, right? It has to be the unconditional probability of B. So it doesn't matter that A has occurred, because they're independent. And therefore, P of B is the answer. We can skip this in the interest of time. So that's basically it. And now we'll go to the two main theorems on which localization is based. So what I want you to pull up is a review of probability theorems. There are two theorems. One is the total probability theorem, and the other is Bayes' theorem. So you can't do robotics without Bayes' theorem. You can't do medical diagnosis without Bayes' theorem. So Bayes was an English mathematician, I think. Those days, most of the exciting new developments were focused on Western Europe and England. Newton, all those guys came from there. A lot of French guys, Okay, so let's start with the total probability theorem. Now, first it looks like another boring mathematical formula, but let's go through it. So given n mutually exclusive events, it's very important, n mutually exclusive. So immediately you imagine the Venn diagram. There can't be any overlap. They have to be side to side. And those n events, they cover the complete sample space.
Okay.
So the sample space is broken down into n1, n2, n3 without any overlap between any n and any other n. On top of that is B, right? So P of B is some subset of it. Okay? Now, probability of B, and you have, so imagine that you have these mutually exclusive events,
Yeah.
and they occupy the entire sample space, and now you're dropping B on it, right?
Okay.
So it is including some of the A's and maybe not some of the, because B is only part of it, right? So it intersects with some of the N's but not the others, right? So you can pick up the probability. So basically this is like picking up the pieces of B. So this can be obtained by one piece plus the second piece plus the nth piece.
Oh, yeah.
And so what is the probability of B can be obtained as probability of B given A1. That means the first piece, right?
Yeah.
And the probability of A1. So piece by piece you're picking it up. Those for which there's no overlap, they will not have a term here. All the ANs, may not contribute. Many of them will be zero, because maybe B is not overlapping with them, so that's okay. We can still have N for generalization, but many of those terms that are not involved in B will be zero. Now, this is a very good example that actually, you understand that, but you still want an example, and I found that this works with students. There are 3 boxes, each containing a different number of light bulbs. So imagine a person sitting here, he's blind, and he's got 3 boxes. And we're going to assume that those 3 boxes are, in this example, such that reach is not an issue. He has equal probability of selecting a bulb from this box, or this box. It's not as if one box is here, so that guy might have a bad back and say, okay, I'm not going to reach. We are assuming that all of them are equally close. And because of that, the probability of selecting from the block box are all 1/3. Which means that PA1, A2, etc., each one of, here there are only 3. There's only 3 boxes. You can't select from a box not in this 3. Then you have to bring them. If that's the case, you have to expand the sample space to include them. So, the first box has 10 bulbs, of which 4 are dead. Which automatically means that if he selects from that box, right, the probability of dead bulbs is 0.4. That's what it means. The second has 6 bulbs, of which 1 is dead. And the third box has 8 bulbs, of which 3 are dead. What is the probability? See, it's a very nice question. He's not telling you which box the person is selecting from. He just says, I know that he has picked a dead bulb. It could be from any one of these boxes. But he's picked up a dead bulb. What is the probability of a dead bulb being selected when a bulb is chosen at random from one of the 3 boxes? And because it's random, you got 1/3, 1/3, 1/3 for this one, and the third one. There are no more. There's only n is 3 here.
Yeah.
Okay, but if he picks from box 1, then these are the problems. They're fuzzy, but they're coming directly from these numbers here. 10 bulbs, so 6 and 4, you agree?
Yeah.
The second one is 6 bulbs, so I believe 5 and 1.
Yeah.
And the third one is 8 bulbs, of which 3 are dead. So 5 and 3.
Right.
And here's the calculation. Let's sit and look at it for a few minutes. Beautiful. So you can put in numbers here. So you have 3 1/3, and then you put in the numbers for the others. I think I made a mistake, and the students never pointed it out back home. I've changed notations on them. So I've got a B. Oh, okay. No. I forgive myself because I wanted it to be box 1. So that's why I changed the A1 to box 1, box 2, box 3. Because then it ties in directly to the problem. And it turns out to be 113 by 360. The beauty of this? Never calculate the fractions. I tell my students in America, they immediately go to the calculator and they get weird numbers for this. It's nice to leave the answer like this. It means there are 360 ways in which you can pick a bulb. Right? And the answer is 113 for this problem, the dead bulb. What about the good bulb then? It has to be all the remaining, right?
Yeah.
So it's nice to leave it like this. Why would you calculate decimal digits for them? Because it destroys the whole beauty of the answer. So there are 360 ways of picking a bulb, of which 113 happens to be the dead bulb. So it's not a very good brand of bulb, you can tell. Because 113 bulbs are, useless out of 360. Yeah, so I pointed out that the 1/3 doesn't have to be the same. In this example it is, but in general it can be maybe one box is closer and there's 40% chance of picking from there. The other 2 are 30%. Maybe the one in the middle, 40%, 30%, 30% because you tend to pick from the one in front of you. So you can change the problem accordingly. It's like those magicians who do card tricks. They want you to pick a card and they're always pushing out one. And the person tends to pick that. So it's like a bias. Some of those card tricks are fantastic that you see on the internet. You don't know how they pull it off. But no, we won't go through the second example. You can go through that and there's more tricky versions of the problem, but the basic fact is total probability is a very useful theorem. Now we come to the big guy, Bayes theorem. So this is the beginning of it. So it's so simple. This is it. But it comes from PA intersection B, the probability part, right? We did this. PA intersection B is the probability of P given A times P of A. But of course, I can write that also as P of A given B times P of B.
Yeah.
So back when we defined it, right? We defined P given A as PA intersection B divided by P of A. But we could also have defined it the other way around.
Yeah.
And what he does is, in both cases, he solves for PA intersection B, so there are 2 ways of expressing the result. Then from that, he decides to pull out PA given B. He could have equally well have pulled out P B given A, but he decides to solve for this, which is equal to this by P of B. So this is Bayes theorem. You get that? He chooses now A, B, B, A. What does it mean? You'll see now in medical diagnosis it has a very specific connotation. But right now you could have written P, B given A, and the only difference is B and A will switch positions. A will be replaced by B and B will be replaced by A. But right now it doesn't mean anything. A, B, what's the difference? We'll see now. And this is the classic example which I got from him. So this guy is another great educator. You should go look at his YouTube videos. 3 blue, 1 brown. Fairly young fellow, but fascinating videos. His the way he draws the graphics and the animation. I don't know how he does it. Python? So you can use Python to graphics? Really? What software is that?
He just said he uses Python
To do that with libraries and all that. It's amazing. Hey, you should check out this. The three blue brown. That guy does, beautiful YouTube videos. 3 blue, 1 brown, Grant Sanderson. Have you heard of this guy, the mathematics guy? Originally from Bangladesh? Huh? Do you know him? There was this guy, Khan Academy? Khan Academy. He was teaching his niece by YouTube videos, right? From Boston to LA. And Bill Gates happened to see it. And then he immediately told him that, he's willing to pay him to create that, professionally. Okay? So this guy used to work for Khan Academy, like the main guy, Khan. And then he broke off and started his own thing. The Grant Sanderson. 3 blue. His website is 3 blue, 1 brown. I don't know why he uses that, but So similar to the Mathworks guy. Beautiful animations. So this is the classic example. Do you have cancer? Do you have AIDS? Hopefully not. Don't get depressed, but these are the commonest examples. So say where you live, 1 in 1,000 actively have COVID-19. So in that area, 1,000 of the people have COVID. Right? So that number could vary, right? Depending upon, maybe in a city it could be more, in a village it could be less. You feel fatigued and have a slight sore throat, so you take a test, get a positive result. Get a positive result, that is condition B.
Okay.
So I got a positive result, but does that mean I have COVID? So P of A is have COVID given the positive result. And that's not necessarily true. That when you take a test and somebody says you have diabetes, it's not 100% true. There are 2 categories, false positive and false negative. So false positive means that the test said that you have it, but you don't have it, right? False negative means you have it, but the test said that you don't have it. So both are positive. We think of a test as perfection, 100%. It's really not. Every test has a false positive and a false negative. Any blood test has a false positive and a false negative, right? So, you learn the test has a 1% false positives. You know what that is? 1% false positives. That means they have got a collection of people who have COVID, right? Who have volunteered to take. They know by other means that they have COVID. Other tests have confirmed that they have COVID. Of them, 1% is false positives. Thank God the number is small, right? If you have 50% false positives, you throw away the test. Because why would you use a test where you can guess? Right? You can just say, you have it, you don't. And 10% false negatives. Now, the beauty is, based on the threshold for the test, every test has a threshold. They're looking for a certain blood count or whatever. By changing that number, you can cause this to increase, but this will decrease. Or vice versa. If you're willing to take a higher 1%, see, it depends on which one is worse, right? And they always tell the story, right? Let's say you have cancer and you get a false positive. Is that bad? Or you don't have cancer and you're told you have cancer? Now, you would prefer to be in this second category, right? But some people have a trauma. When you're told you have cancer and you go through 6 months thinking you have cancer, right? That's also bad. A false positive is bad also, right?
Yeah.
Maybe of the two, you would eventually settle for this because it turned out that the test was not correct. But both are bad actually.
Yeah.
So both of them are actually bad. So that's why they try to bias it so that these two numbers are close to each other.
Yeah.
You cannot make it 0, 0. It's impossible to make it 0, 0 in this world. No test is perfect. Now, fingerprints. Is that perfect? No. It's close to perfect. What about iris? Bit better, still not 100%. So in life, I don't think you'll have a perfect test because, face recognition. So it's high number, but it's not perfect.
The videos of like twins doing like on TikTok, like twins both.
TikTok? Yeah, right,
both
exactly.
of them can-
Sure. Yeah. So it's possible to fool it. So it's not 100%, there won't be anything. So he asked it in the form of a quiz, and the answer happens to be 85%. You learn the test says 1% false positives, 10% false negatives. What's your best guess for your chances of having COVID-19? It has to be high. It can't be like 10.3 because then it's useless. So how do you calculate that? You can solve a problem by Bayes' theorem like this, but that's only because the choices are few. Otherwise, diagram will take more than one page. But when you're learning, it's good to have this. So solution. So this is probability of the disease, right? We're getting these numbers from here. Probability of the disease, 1 in 1,000. That's right. So this is 0.001, not as a percentage but as a fraction, and the remaining is 0.999. So you take a person or you take a population alone, and you have these two categories. Then of these, right, given that you have the disease, you test positive, right? Where is that? 1% false positives, 10% false negatives. So true positive will be 0.9. 90% and 10%. I'm getting it from here. I'm not making it up, but here it is, 10%. So that breaks down into 90 and 10. Is that okay? And then down this branch, it is you don't have the disease. So if you don't have the disease, it has to be this category, false positive category. So you have 1% and 99%. And then it's very easy because the numbers are right here. P of positive given disease. So you're on this branch, right? Given that you have the disease, probability of P, that's number. Probability of D is probably the disease, you already have it here. So you can calculate this and it turns out to be 0.0264 or 8.26%. Probability of the disease given that it's positive. So I just made a note here that don't get confused between this P and this P. This is positive, this is probability. So it's a very powerful terminology. And now we're going to change the notation because A and B is very confusing. Even D and P is very confusing. So we change it to the standard Bayesian terminology. So on the left, you have probability of a hypothesis. So when somebody says you have COVID, it's a hypothesis. When somebody says you could have diabetes, it's a hypothesis. So what is the probability of a hypothesis given the measurement? The measurement is a blood test. The probability of the hypothesis given the measurement is exactly the same thing as this. It's the same thing except that we're giving more meaning to these symbols here. So probability of the hypothesis given the measurement is equal to probability of the measurement given the hypothesis. Just check this out. This relates to this problem of Grant Sanderson so perfectly because the measurement is the COVID test.
Yeah.
So given the hypothesis, that means if you have it, then how do the tests show up? Probability of the hypothesis over probability of the measurement. Right? What is the probability of the hypothesis? That's the general population. 1 in 1,000, right? So such a simple theorem but so powerful. And it not only medical diagnosis but localization and mapping, SLAM, particle filtering, you name it. It's all based on Bayes' theorem. Lots of other things also. So they have a separate area called Bayesian estimation that is based on Bayes' theorem. So SLAM and localization are not the only areas. It's used. Probably the guy Bayes did not know that it would take off like that after his death. So we have special terms. So H given M, right? This one. So this is the posterior meaning after the measurement, right? Don't you have a better idea of whether he's got it? Otherwise throw away the measurement, right? If you take a measurement, it has to give you a different idea of the probability. That's why you're doing the measurement. If it's a random measurement, then it won't. So typically when you measure, you get a better idea. When you measure the localization, the position of the robot by GPS, so by the way, that's where you're going to use it. Remember the looking up, counting steps, and then you look up. The look up is where you're going to use the Bayesian theorem. Okay? So the probability of the hypothesis where the robot is after a GPS reading is given by the probability of the GPS reading given the hypothesis. So how are you going to get that? It's because let's say you have a map, right? And so forget the GPS reading. I look up, I see a Kentucky Fried Chicken. So doesn't that give me an idea of where I am? Because I have a map and I saw a Kentucky Fried Chicken. I saw a bathroom in a hallway and I kind of know where it is on the map. I was looking at my cell phone, not paying attention. I looked up, there's a bathroom there. So the probability of the measurement given the hypothesis is known from the map. You know that you're only likely to see a bathroom in one corner of the building, right? Or down this particular hallway. So that's what this is. It's the flip. It's the opposite of this. Because you've done all those COVID tests on people who have COVID, who are known to have COVID, then you have this information. Just like the map also gives you the same information, right? So the probability of the hypothesis, right? And the probability of the measurement. So the left hand side is known as posterior, means after the measurement. PM given H, that is, you have a sample of people who have COVID. How many false positives and negatives? That's known as likelihood. And then PH is a prior probability. Remember the 1 in 1,000? So the prior probability of the hypothesis. And then P of M is the probability of measurement. I'll tell you how they get hold of this, right? How do they resolve this denominator term? So conducting the test should provide us better information about the hypothesis. Yeah, obviously. So now we're ready to get into localization. Maybe after we do that, we might take a short break. So that document is, Bayes rule localization connection. Something happens when I do a PDF on this. So pull up the Word document. I also uploaded the Word document. Strange things happen. I believe I posted that also. If not, let me know and I will post it again. So again, we don't need to go through this in detail. I told you there's two phases of localization. You take steps, which is inaccurate, and then you look up, which makes it accurate, right? So the lookup, the so-called correction, is done using Bayes theorem. The the action, which is steps, is done slightly differently. We'll get to that. So these are the two steps involved in the localization process. The lookup is done by using the Bayes theorem. The other one, steps, is done using total probability theorem. And let's get into it now. So again, I'm reminding you of the terms in the Bayes rule. So here, our event H, right? The hypothesis is going to be replaced by the probability of the robot having a certain position along the line. So because we can't get into the multi-dimensional estimation, we just assume a robot is moving down a straight line in order to simplify it. And so only one position is involved, right? So what is the probability the robot is at 2 meters from the starting position? That's what you mean. So that is equivalent to the H. A one-dimensional version of the more general problem. Now, for a robot moving in a plane, the pose is made up of a total of 3 numbers. So we'll have to do some kind of a matrix formulation, and it gets very complicated. And we're not going to do matrix algebra here, but there is a matrix version of that. Okay, what is this M here? Think of event M as a single sensor measurement. So it could be you looked up and your camera, when you decomposed the image and did perception, it said, hey, Kentucky Fried Chicken.
Yeah.
Or it could be a GPS reading. So the left-hand side is the conditional probability, which can be verbally stated as the probability of the robot having a certain position in time t, given the sensor provides a certain measurement at time t. So there is a conflict, right? because you have counted steps, and that tells you you're somewhere, but it's inaccurate, you know that.
Yeah.
And yet, when you look up and see the Kentucky Fried Chicken just 10 meters ahead of you, that's also telling you something about the position. So how do you sense a fuse? You do so using Bayes' theorem. So the probability of the robot having a certain position at time t, given that the sensor provides a certain measurement at time t. Rarely with the measurement and your understanding of where you are coincide, because that's not how the world is. And now it's your job to bring them together. Don't just average them. Do it using Bayes' theorem. So the sensor error, you looked up, camera, scene, perception, right? There is error in all of those processes. So you have to model that whole thing probabilistically. Even a LiDAR measurement, there could be error. So P of H is replaced by equivalent to P of xt at t, your position is L from the starting block. And we're going to simplify it by throwing away all this xt equals L. Just the probability of L, we understand, means that probability of xt equals L.
Yeah.
Probability of H given M. So that was on the right hand side. That's basically probability of L getting the measurement, right? IT. That is what is the probability you are at L given that you have made a measurement IT? What is the probability you're you're at L given that you're at IT? So it is slightly different, isn't it?
Yeah.
Because this came from your past, counting steps. But now you're saying probability of L given, I know you have a measurement.
Yeah.
So hopefully your perception or your understanding of where you are is better than that, because you've taken a measurement. Unless the measurement is totally useless, this should give you a better idea. The probability has to go out, right?
Yeah.
Because odometry was falling apart, but now you took a measurement, so probability of L given the measurement should be better than that. So conditional probability. Conditional probability of robot location, over here. Now, this is a tricky, like a digression, but it's needed. So little p is probability density function. So probability density function is continuous. It tells you what is the probability at 1.12 meter, 1.123, 1.12, it's continuous. Big P is discrete.
Mass.
Yeah. Typically, when we implement our digital computers, you can't do continuous anymore. You can't integrate. All those things are good in calculus,
Yeah.
but you can only have what is the probability on this square, on that square, and so on. So then it becomes capital P, because it doesn't make sense to do continuous. A computer can do 10 million points, 100 million points, but it cannot do continuous. A computer cannot do continuous, right? So therefore, capital P makes more sense. So that's, we still stick to the capital P. Then no, in fact we have switched to capital P now permanently. So this is what we have, right? And then I again remind myself, how would I get Pi given L? Well, because I have a map, right?
Yeah.
I know what measurements I'll get at different points, where I should see a Kentucky Fried Chicken.
Yeah.
So I know that. So therefore, that's how I get this side. It's just like, okay, I get 100 COVID patients. I know they are COVID infected by some other means. And then I find out how the test is doing. That's exactly what this is. So that comes with a map in this case. So did you know that? In a cell phone camera, you turn on the thing, right? And they can give you a location. How do they do that? So Google has taken all these images. This worked even in China, by the way. So the moment you turn on your cell phone, right? If you're not knowing whether you should go this way or this way, sometimes you don't have a sense of north, south, east, and west. You just turn on your camera and focus it on the building, and they will tell you precisely where you are. So now, of course, they haven't photographed every building in every village in the world, right? But most of the major cities, you just have to turn on your cell phone, and if you use that app, it will tell you precisely where you are located. So that's what this is. The P of I given L. In a robotics example, you cannot be sure that the map is correct.
Yeah.
So the map would have changed, and maybe you're working off an old map, right? Or maybe a tree fell across the road.
Yeah.
So you can't move, but on your map it says everything is fine. So you do have to compensate for the fact that no map is permanent. There is no map in the world that's permanent, because things may change. A dog may have walked there, they may have put it on the map, but the dog then went away. So this is known as multi-sensor fusion, by the way. The steps, the odometry is fused with the GPS or LiDAR. Turn on the LiDAR and look at the thing around, so the scenery around you. That's known as multi-sensor fusion. You can add IMU to it. You can add optical cameras to it. So the more you add, right? So all of them, the optical camera, the GPS, they are all done by this equation. So Bayes' theorem is used multiple times. The step counting can only be done with IMU or the odometry. The GPS, turning on LiDAR and doing a slam, all that is done by Bayes' theorem. But they're happening so it can get quite complicated because you may get odometry up to this point, right? And then IMU is running in parallel. You have to find a way of reconciling them first. Then you take a GPS reading, or you look up and look at Kentucky Fried Chicken. So that may happen at different times. So you have to apply Bayes' theorem twice at those points. So there's a lot of coordination involved. It's a very complicated program. Multi-sensor fusion is actually quite complicated. What about this? How do we get the value of this? So we know how to find this, right? This is map. I know what I should see here. If I'm at L, I know what I'll see. So that's what you're calculating, dependent variable. We know what that is. That's, what is the probability of this location?
Yeah.
That's going to come from odometry.
Yeah.
So this one is going to come from odometry because you have a rough idea of where you think you are, right? You're trying to improve it by running it through Bayes' theorem. Now this one is a mystery. How do you get probability of the measurement? What does that mean, probability of the measurement? Well, it turns out you don't have to worry about it. You know why? Because if you're doing discrete, okay, the left-hand side is a probability. If you evaluate P over all the i's, right, then you should get 1, right? So suppose I evaluate the left-hand side and ignore this. Let's say I only use the numerator of Bayes' theorem, right? But I have that for every possible value of I, right? Should the left-hand side add up to 1? If I ignore this, I don't know what it is, so I'm going to act as if it's 1 for now, and I calculate the left-hand side, right? Finally note that the denominator P of L does not depend on L. Finally note the denominator P of, looks like L, right? So essentially what I was saying was, if you can evaluate the left-hand side for all possible values of I, you should get 1. So if you first evaluate it without the denominator, then you can sum up all the left-hand sides because the sum of all possible probabilities on the left-hand side should add up to 1, right?
Yeah.
If you get that number, then you can go and divide each one of those numbers by that total. And it will become a probability. So therefore, you have got away by not having to specifically find the number for capital P of I. Because if you evaluate the left for all possibilities, right, then essentially, if you add them up and they are not 1, you can force it to be 1 by dividing by the sum. And then you do the same thing on the right hand side and you avoided having to find the denominator specifically. And finally, the missing one that I said was odometry, namely this guy. Let's talk about it, okay? How do I get that? So I have the odometry data. That's how I'm coming up with a guess for P of L, right? We did some odometry earlier. When we derived the kinematic model for the differential steered vehicle, I said that basically you can, if you count the number of takes, you can figure out where you are, right? With some error, because wheel slip, one tire might be overinflated, so there's going to be some error. That's why you're looking for a GPS reading, otherwise you'll run for odometry all day, right? So, then how do you get the probability of L given one single result for odometry? And here's the argument, it's actually quite a nice argument. It says, what's the probability that I'm on this tile, given the odometry? Given the odometry. So it says, maybe I could have got to, so instead of odometry, let's say steps. I've taken 10 steps, right? What is the probability I'm here? So it says, I could have got here from there, from there, from outside the campus. Now, of course, don't laugh, because theoretically, maybe somebody picked it up in a plane and dropped it off here, and you're looking at the steps. So, but in practice, that's absurd, because there's only some choices of tiles which, with the 10 steps, could have led here. But you're saying, no, there's only one choice of tile. Why are you saying that there are multiple cell choices that with 10 steps got you here? Remember, the step can be long or short, right? Odometry is imperfect. People get tired. They count their steps, but now, they're taking very short steps. So that's why total probability comes in. What is the chance, given that odometry says, it's recording this, I could have got to this tile, from that tile, this tile, this tile, this tile, this tile. Total probability. Because remember the boxes of dead bulbs?
Yeah.
How do I get a dead bulb? What is the probability of here on this tile? I could have come here from all the surrounding tiles. You don't want to go completely crazy and say I would have got to this from a tile in Andhra, because it's not likely, right? So typically what they do, and this technique is not Kalman filtering, but it's called Markov localization, which also uses Bayesian theorem. They say they keep a certain number of active tiles, they never let anything die. So you're carrying all these probabilities around, and you're saying, okay, what's the chance I came here from that one, this one, this one, this one? And they have their own probabilities. Like remember the dead bulb?
Yeah.
So the dead bulbs were different, right, in the different boxes. So they have their own probabilities, and then we use the recorded odometry or number of steps to say what is the chance. Obviously, if it's further away, there's less chance, right? It will contribute less. But it is contributing. It is contributing to the total probability, but not much. The strongest are the ones probably that are closer.
Yeah.
So finally, when it's time to make a decision, you will pick the one that is the longest or the highest probability, the biggest probability. But no, you're just using this to correct through looking up. So you just carry all these probabilities forward.
Yeah.
So essentially, that's what Bayesian theorem looks like in terms of actual implementation. Now, one form of it is SLAM, one form of it is Kalman filtering. We'll focus more on Kalman filtering because it's the most popular method there is. Maybe at some point in time it will be overtaken by SLAM. There's a lot of computation. Kalman filtering, there's the least amount of computation because it's like a one-step update. Each time it's a simple one-step update. SLAM is a lot of work. Particle filtering, a lot of work again. Because the particle filtering does not use any probability function. It keeps all the data. You see, when you turn on a 3D LiDAR, you get what is known as a point cloud, and it keeps all of that active in its memory. Whereas Kalman filtering, Gaussian, and one estimate. You're just moving one estimate, and you'll find out that Kalman filtering assumes one estimate for the robot's location, and it's trying to massage it as you go. That's why you can't afford to lose that estimate. Whereas the other techniques, they offer more redundancy, but because of that, you also have to put in a lot of effort. Nowadays, the reason that particle filtering and other such techniques are increasingly gaining ground is that computers are so much more powerful and they have so much more memory than in the old days. I remember in the old days when I was an undergraduate student, well, certainly even as a PhD student, there were these huge disks and they would fill up, and then you would have to figure out what you want to delete because it's too costly to buy another one of those disks. So essentially you have to manage your data. Nowadays people get rid of their cell phones. Maybe they don't even transfer information, or maybe they do, but actually they do because there's a transfer, and they never delete the old junk stuff. So they carry all the WhatsApp and Instagram videos, and still it seems to be okay. It doesn't fill up the new phone, because earlier we used to go for 128 gigabytes. Now 512 is not that much costlier. Soon you'll get a phone with a 4 terabyte, disk space, memory space. So people just carry the old, nonsense. You don't even bother. When I was a PhD student, you had to figure out, okay, I think I don't need this. If you needed something, you try to print it out, but you can't print. You can print out programs, but you can't print out data, right?
Yeah.
Because there'll be pages if you're working in this kind of area. So he took a chance and said, okay, I'll lose this to create some space. So, but nowadays, that's no longer a constraint, and so particle filtering and other methods like that are increasingly being used. All right, so I think we take a quick break, and then we move on to Kalman filtering. Yeah, this is very important. I said it in words, but let's read this. The same location L can be reached from multiple earlier locations with the same encoder measurements. You have to get your head wrapped around that concept. The same location can be reached from multiple earlier locations with the same encoder measurements. Do you agree or not? With 10 steps, I can reach this from multiple locations. I can take long steps or short steps. And that's what is being used in the total probability. Is there an equation? You don't want the integral form? There is it. So belief is basically the probability of LT minus 1. Let's spend a few minutes before we get into the break. So I know it's new terminology, but somewhere here I said belief is the same as the previous year. Belief is the old probability, So belief at LT is belief, or P at LT. So here it is. So I hope you get a sense of the dead bulbs in the boxes here. That's all I want you to do. I don't want you to go any deeper than that. So the left-hand side, what is the probability that I'm on top of this tile is all LT minus 1, all the previous positions, right? What is the probability of being in all those previous positions? All of them have been updated by the Bayesian rule, so they are fresh. So all of them multiplied by the probability of being in LT given that you're in that previous state and the encoder 10 steps. So this is your total probability theorem. This is exactly it, conditioned not for the dead bulbs problem but for the robot motion. So the details are all there if you want to look at it, because these documents are in Teams and you have access to it. But again, to summarize before we take a break, this is total probability. Steps, knowing that the same odometry can get you to this tile from different places. I told you how we get rid of PI. We obtain the left-hand side for all values of I. And then divide by the number to make it a probability. And this is like your COVID test. Does he have it or not? So you open your eyes and say, okay, I see this building here. So, the probability of being there. Why isn't that 100%? Nothing is 100%. Because you may look at the same restaurant from a slightly distance, so there is some error involved and you have to put that in the form of probability. It's not certainty. Just like your COVID test, right? Remember that? In the original example, Bayes theorem, it was not certain. So there has to be a probability attached to it. Okay, I think we're done with the prelims.